Okay, well, thank you. It's quite a challenge to give a lecture like this where the audience ranges from, Steve Chu, a Nobel laureate who's working in this field, to my mother. And I'm sure I won't be able to make it both interesting and understandable to everyone, but if I fail, Steve, I'm sure after the talk my mother can answer questions for you. So, as the old man of the group, what I'm going to do today is give the background of an introduction to Bose-Einstein condensation in a gas, the developments that led up to us creating it, and then sort of turn things over to Eric and Wolfgang to talk about the experiments then more. Some amplification on this, but more than on the experiments that the three of us have done with Bose condensation since it was created. Now, this starts at the very beginning worrying about temperature, because a key issue of this is getting things extremely cold. So just remind you what temperature really is in a gas. You've got atoms flying around, and their temperature is really just a measure of their speed. And so if you cool them down, you're really just slowing them down. And when you think about temperature in that respect, you realize that there's a lowest temperature you can go to where all the atoms have stopped. And so from physics point of view, we have this absolute the absolute or Kelvin temperature scale where 0 really means something, and that's this absolute 0 down here. Now, we live way up here at, and absolute 0 is down there at minus 273 Celsius, and so a big part of the experiment here is to get things way down to absolute 0, or extremely close to it. And it's interesting to note that this Bose-Einstein condensation can never occur in nature, because the coldest spot occurring in nature is the depths of interstellar space, where it's still 3 degrees Kelvin. And so that's millions of times hotter than what we need to work at. And so when this stuff exists, it really only can exist in the laboratory. Now, of course, we're not just trying to set records for low temperature. The reason for trying to get these very low temperatures was to create this material, Bose-Einstein condensation. So let me talk about what that is. If you take a bunch of gas atoms and you put them into a container, and this is, physicists for a long time have known that they can't have any arbitrary amount of energy, speed rolling around in this container. There are only certain discrete levels, certain amounts of energy they're allowed to have. But in a normal sized container, these are incredibly close together. And so normally you can never notice that there are little gaps between them. That's by normal circumstances. I mean, when things are reasonably hot, which by my standards is, 10 millionths of a degree above absolute 0 or so. And in that case, they just run around in there just like little balls like we're used to thinking about. But what Einstein's equations realized, as pointed out in the introduction, or what came out of Einstein's equations, were extending the work of Bose, is that as you get atoms colder, much colder now than we're talking about here, their quantum waviness gets larger, so-called de Broglie wavelengths. And in fact, at very low temperatures, these get much bigger than what we think about the normal size of an atom. And if they get so large that the de Broglie wavelengths of the different atoms start to overlap, then what Einstein predicted was that a very strange and profound thing is going to happen. Then, instead of these atoms being distributed over many of these enormous number of closely spaced energy levels, they'll a large fraction of them will start in some sort of quantum lemming-like sense, decide that it's time to all jump down here into the lowest allowed energy state or energy level in this container. And this is what we call Bose-Einstein condensation. And the temperature scales for this to happen are something 100 nanokelvin, 100 billionths of a degree above absolute zero. Now, as was pointed out in the introduction and is often presented this way, this was sort of the history of Bose-Einstein condensation. Back in work of Bose and Einstein here, and then this giant 70-year gap until we made it. But this is actually not really the proper perspective. And so I want to go into detail about what the right way to think about this. There's a lot of history in the middle here. And first, we have superfluid liquid helium and the idea of Fritz London that this may have been a manifestation or maybe due to Bose-Einstein condensation, even though it's in a very different system than Einstein was talking about. Einstein was talking about a very dilute, non-interacting gas. Here we have a dense liquid. But nevertheless, they as London first realized, although it was debated for many years, they are, in fact, connected. And London also brought out what's one of the most fascinating aspects of Bose-Einstein condensate as a material. Namely, it's a macroscopic quantum system. So it's a material where you can have a large enough amount of stuff to see quite clearly, and yet its behavior is completely governed by these strange, bizarre laws of quantum physics, which are normally safely confined deep inside the atom. In a Bose-Einstein condensate, they appear rather dramatically for everyone to see, as you'll see later in the subsequent two talks. So there was liquid helium-4, and then superfluid helium-3, of which Osherov, Lee, and Richardson, of course, received the Nobel Prize for, another manifestation of Bose-Einstein condensation in a liquid. But in terms of our particular work, then you have to go a little later, and things really start to heat up. First with the proposal of Nazanov and Stwally that in 1976, that hydrogen had some special features so that it might actually be able to be made into a Bose-Einstein condensate gas, like Einstein was talking about, and maybe it wasn't a completely theoretical abstract concept that could never be really realized in the lab. And that got started a whole large number of experiments. The most prominent groups were Severa and Walraven in Amsterdam, and Kleppner and Greytag at MIT, but quite a number of other people working on this. Did a lot of experiments, developed a lot of technology, I'll say a little bit more about later, in the pursuit of actually making Bose condensation in a gas in hydrogen. And that went throughout the 80s and into the 90s. Now, at the same time, and quite an independent parallel effort, though, was laser cooling and trapping. And this started back in 1980. And again, there are a large number of participants who've contributed to this. I'll just note a few of the most prominent ones, particularly if they're my friends in the audience. But really, Dave Wineland working with ions, and then, of course, Phillips, Chu, and Kohn Tanucci received Nobel Prize for laser cooling, work in developing trapping, holding atoms with laser light, Chu and Pritchard and others. And even we had a little bit to do with this subject. So all of this, there's a great deal of work on this subject also during the 80s, laying a lot of groundwork, technology, techniques, understanding of how atoms behave at low temperatures. So basically, we put all these things together. And so I'm going to just touch on a few of the most important features that sort of we took away from the work in hydrogen and cooling and trapping. and brought together to make Bose-Einstein condensation as we did. And okay, the first one from hydrogen probably is just the whole general goal of that Bose-Einstein condensation is in a gas is something that it's not so crazy to think about actually doing, and it would be really interesting to succeed. And then, but more important than beyond that, they did all these experiments trying to make Bose-Einstein condensation in a gas. And out of those experiments, they didn't succeed in making Bose condensates until just a couple of years ago. But all during that decade, they did a lot of experiments that, on the one hand, looked like failures. They didn't get the goal they wanted. But on the other hand, they were really very successful in telling us a great deal more about how atoms behave and providing useful guidelines as to what the really important physics was. And so from my point of view, looking at this, the key idea was that they, after you looked at all their experiments and results, it made the point that hydrogen really didn't have this special feature that it could uniquely form Bose condensates. In fact, it became clear that any Bose condensate you made in a gas was a metastable state. Basically, all those cold little gas atoms really want to turn into a little ice cube. And there are many, many ways nature finds to get from a gas to an ice cube. And you have to prevent, the real experimental issue is preventing this loss of metastability, turning into an ice cube. And that's really much more important than worrying about the temperature you actually need to reach to get Bose-Einstein condensation, which is actually higher in hydrogen. But when you look at all these issues, it became clear, because we had all their experimental results to look at, that maybe hydrogen, first, it wasn't special, and maybe wasn't even the best atom. And so that led us to think about doing this in other atoms, like alkali atoms that we used. Other important things from this, they developed this technique of magnetic trapping and evaporative cooling, which we shamelessly copied and worked very well to get there. And then finally, I think these, Eric, Wolfgang, and I would all endorse these features. This one is maybe unique to me, is just also looking at these experiments, I sort of personally saw that they were getting enormously complicated, massive, using traditional cryogenic refrigeration and so on. And so a big motivation for me personally was just the idea that, okay, I thought, frankly, they're pretty close to Bose condensation. They'll probably get there. But we had an approach which might be a lot simpler, easier to duplicate and use. And it was just the motivation of trying to do things in a way that could be, much more widespread, easier for people to do, sort of just a simpler technology, not any basic physics. From laser cooling and trapping, then, we also had a lot of useful things from that, a lot of techniques I won't get into too much detail on, but some of the key issues are it gives you a very good way to get a very high phase space density. This is the product of coldness and denseness, and that's really what you need to make Bose condensation. They got very, very low temperatures down to microkelvin. They demonstrated lots of nice optical techniques using light to look at your samples to see, you could tell lots of details about the density and temperature, what the sample was doing by taking pictures of it, essentially. And it could be quite a cheap and easy and reliable way to get atoms very cold and very high phase space density. And that's important if you're going to use this as a first step in trying to do something more, which was the case here. And then also, in the process of studying these, we learned there are various things about the bad photon processes you need to avoid if you want to get things very cold. So that gave one the idea of combining these two techniques to use some of these ideas where you didn't require photons. So that was this decade of work by lots of people that laid out these points that allowed us to be the starting point to put them together to really make Bose condensation. As Eric so nicely put it, these people really plowed the ground that then we sowed. Okay, so now let me talk about how it's actually done. This is the cartoon of our particular apparatus. Wolfgang's looks a little different, but I'll show later, but the techniques are basically the same. You have a vacuum chamber. In our case, it's a little glass cell, about the size of my fist. Here's the whole picture. Pump out all the air. You have a little bit of the atoms that you wanted to cool. In our case, they're rubidium bouncing around inside here. You send laser beams. So you can send laser beams into this cell, the red things, and then the green and the blue here are just coils of wire for making magnetic fields. And so the technique that we use then, and I'll talk about in detail, is this three-stage process of laser cooling and trapping, magnetic trapping, and then evaporative cooling. So how do these work? Well, the first step then is this laser cooling and trapping. And there's a bunch of subtleties to this, but the basic force, the most important force that you're dealing with there, is just the little momentum kicks you get when a photon bounces off an atom. And now I can go to the interactive part here. And so the little particles of light we call photons basically will just collide with the atom. And on this scale, atoms are like big fat bowling balls, and the light is like a little table tennis ball. But if you bounce enough table tennis balls off a bowling ball, you can give it a big kick. And the great thing about lasers is you can get a lot of light coming out. And so this gives you a substantial force that you can use to push around atoms. So that's the basic force that we're using. Now, but just pushing them around isn't good enough. We've got to get them cold, which means we have to slow them down no matter what direction they're moving. And so for that, we use something that Steve Chu invented called optical molasses. And the way this is now, picture, this is our little glass cell here in 2 dimensions. And so we now have coming into this from all 6 directions laser beams. And we've got our rubidium atoms zipping around in here. Of course, real atoms are a lot smaller than that, and they're moving at something like 1,000 kilometers an hour. But you get all the basic physics is in here. It's just slowed down. So these atoms are zipping around in here. But they only scatter laser light if the light's just the right color, that their resonance frequency here. And so if it's way to the red like it is now, they just go right on through and the light doesn't, and they completely ignore the light. Or if I go way up here to the green, again, they don't even notice the light's there. As I get closer to resonance, though, now they start scattering the photons of light. And I'm not showing all the photons bouncing off. That gets too messy. But you can see the effects. And here they're speeding up. And the reason the light is affecting their speed is because of the Doppler shift. And so if I'm up on the green side here, the Doppler shift tends to actually speed them up. Of course, that's not what we want. So what one needs to do is very carefully, this is a key part of the experiment, very carefully tune the laser so that its color is just to the red of the peak of the atomic resonance. Now as an atom comes in here, it basically always feels the light that's hitting it in the face the most strongly. And so no matter what direction it's going, it preferentially scatters photons that are slowing it down. And so it can, those scattered photons can slow the atoms down, and they can pile up in the middle here. And after a little while, this takes a few seconds usually in the experiment, you end up with a bunch of atoms piled up here in the middle, held by this laser force. Now, actually, the way I got into this business was playing with laser cooling and trapping, and we were studying both how to make it cheaper and simpler, but also we got into studying what was the limit on how dense and how cold you could get atoms in a laser trap like this. And what we found is there were several kind of exotic atomic physics processes at these very low temperatures, but they all involve the photons. Now, the photons are sort of like fish in that they're very nice to have when they're fresh. When they're fresh, they come in, you can use them for cooling and trapping the atoms. But if they hang around if it's been, their photons have been hanging around too long, then they really start to get unpleasant. And the way these photons can hang around too long in this case is they can bounce back and forth between these atoms. And one of the obvious things that does is every time it bounces off an atom, and you can see if you look very carefully, these are still jiggling around a little bit. So that's limiting their temperature. And there's other things they do that are even worse. So that led to the realization, that what we ought to do is get, just like old fish, we should throw out the old photons. And so that's easy enough to do. Once you've got these nice cooled and trapped samples, you just turn off the laser light. But then these atoms are very cold. They're not moving very fast. They just fall, thud, hit the bottom of the apparatus. They don't make quite such a loud thud, but and they're heated up again. The experiment's over. So you need a way to hold them very gently to keep them cold. And that's where magnetic trapping comes in. And as I pointed out earlier, magnetic trapping had been developed by Dave Pritchard and the hydrogen trapping people and Bill Phillips and others. And it just turned out it was a whole lot easier to do if you'd laser cooled these atoms because they were moving so slowly, it didn't take very much magnetic field. So that's where, in that picture I showed of the apparatus, those blue and green coils come in. So we turn off the laser light, turn on current through those coils. They make magnetic fields. Those magnetic fields interact with the little tiny magnets. These atoms are little magnets. And so those magnetic forces just hold them there very gently. And it makes a wonderful thermos bottle. They're very cold. They're not heating up. They're just sitting there. And so once this happened, it worked great. It was easy to do at much colder atoms, trapped atoms, than people had gotten before. And this inspired us to then follow the lead of the hydrogen trapping folks and try to do evaporative cooling of these atoms to actually go after Bose-Einstein condensation. Now, that was in 1990, and it took a few years. And during this time, so Eric and I, and then Wolfgang, Randy Hewlett, Steve Chu working in different kind of trap, started working on how to make this evaporative cooling to Bose condensation work. And we actually, certainly in our group, a lot of what we did over these years was actually just to study atomic physics collisions. There's some good collisions that you have to have for evaporative cooling. The atoms have to share the energy. And then there are bad collisions which cause atoms to be lost from your trap, and that hurts things. And so at the time we started this is, how the size of these processes at these extremely low temperatures was very unknown. And so a lot of it just had to measure it, find out what was important, what wasn't important. And basically it turned out our original hunch was right, that these were very frequent. There were lots of good collisions. The bad collisions weren't too bad. And the most important one of these bad collisions was, for making this work, were hot background atoms coming off the wall, smashing your cold atoms out of the trap. And so with this in mind, one could then design an apparatus to really to make all this work. And the key technical issues were you had to get rid of background gas atoms, which meant making very good vacuums, and that was sort of standard technology. Realized you needed as high a density of atoms as you could get, and that meant getting higher densities out of the optical trap, and that led to developments On optical trapping, the dark spot Mott by Wolfgang and the C Mott or compressed Mott by Eric. And finally, you had to squeeze up the magnetic trap. Once you'd put them in the magnetic trap, you had to turn it up to squish them all together to get as many of these good collisions as possible. And that led to a variety then of different trap designs. Everyone sort of has their favorite. Eric invented a particularly clever one called the top trap, but I'm not going to go into those technical details. Wolfgang and Eric can talk about them if they want. So having put all those things together, we then had enough, a denser sample of atoms in our optical trap to make this process called evaporative cooling work. And evaporative cooling, the concept is familiar to everyone. In your cup of coffee, that steam coming off is the most energetic coffee molecules leaping out of the cup, taking away more than their share of the energy, so the coffee that's left behind gets cold. Same concept applies here. It's just until the hydrogen trapping people thought about it, no one would have thought it was a way to get things extremely cold. So the way it works is, here's your magnetic trap. You dump your atoms in there, and you let the most energetic ones get out of over the lip here, and the others are settling down here, getting colder, and slowly working their way down towards the Bose-Condensation transition temperature. But you can see after a little while this stops cooling, and so what you have to do in the experiment is just what I'm doing in this little simulation. You have to slowly lower the lip of the trap, and so that you're always skimming off the most energetic atoms. And this takes, certainly in the early experiments, the time scale roughly a minute, so just about as long as this little video game. And there's exactly the same point, namely, the graduate students spend a lot of time in the lab trying to adjust exactly how this comes down so that you're left, you don't throw away too many atoms, but you still keep the cooling running so that by the time you get to Bose-Condensation transition, you've got as many atoms left as possible. See how I do here. And I should mention along the way that we don't actually change the magnetic field in these experiments. In order to get very precise control of this, we use something called an RF knife. We use a radio frequency field, and this was suggested by Dave Pritchard, so that it effectively puts a hole in the edge of the trap, that once atoms get there, then their magnets get flipped over and they disappear. So am I getting close here? 20 is a good score on this, by the way, if you go home and do this yourself. All these things are on the web, so all right. Not doing so great today, but come on. Okay, so finally you get to the transition temperature and you get Bose-Einstein condensation, okay? So, but it doesn't actually turn into a little glowing, pulsing ball in your apparatus, so let me talk to you about how we actually look at it. The way we actually look at it is we take a shadow picture of it, you've got a little ball of atoms cooled down here, you send a little pulse of laser light, those atoms scatter the laser light and just make a shadow, and we image the shadow onto a TV screen. So we have this little two-dimensional shadow picture there, and it's really a black and white shadow, and so you can see if the cloud's very spread out in this magnetic bowl. It's not a very dark shadow, and it's very spread out. As the atoms get colder and denser, they get smaller and a darker shadow. So that's what it really looks like, but in our first pictures, we sort of dressed this up, and that sort of set the style for everybody now. And Bose condensation makes pictures like this, where these are three different runs of the experiment. This is actually from the very first observations of Bose condensation, where the darkness of the shadow is in this third dimension here, and the colors are just artificial to look nice. So here we've cooled things down to a sort of by lowering the edge of our bowl to sort of a tepid 400 nanokelvin. So that's 400 billionths of a degree above absolute zero, and just sort of this gentle rounded hill. Here we've gone a little colder, 200 nanokelvin, and suddenly this narrow spire appears. And if we go down as far as we can, then we have about 50 nanokelvin. We could get condensates where essentially all the atoms are in that narrow spire of a few thousand atoms. Now, this signal is exactly what you expect if you think back to that original picture of what Bose-Einstein condensation is. Because in a bowl or potential well like this, the ground state is the most localized state. And so the atoms that are up in these higher excited states are all spread out. They're the ones in that gentle hill. And as the large fraction of the atoms goes down to this ground state, you get that very narrow spire in the middle there. And I'll show you actually in a real data what this looks like as it's forming here. So this is just running, this is 3 times normal speed, but here's our distribution as we're actually evaporatively cooling the atoms. And you can see as you hit the transition temperature then, that very narrow spike suddenly appears. So it's very clear this dramatic phase transition predicted by Einstein here. Getting ready here, it's going to hit it. And so suddenly there's this very abrupt change. So that's the real signal. I guess I have enough time to make one quick point. So although that really is a clear indication of Bose-Einstein condensation, that narrow spike in the density distribution was really what we had been expecting it would show up for sort of the third day we started thinking about doing Bose condensation way back 5 years before. And so one's always nervous in an experiment like this when it looks like it's working better than it really should. That you're just fooling yourself. And so for us, the real clincher that convinced us this absolutely was Bose-Einstein condensation was a signature that we hadn't been thinking about ahead of time, but as soon as we saw it, we realized, oh yeah, that's just what it ought to look like. And so just because we hadn't been expecting it, it was really more convincing to us that we weren't fooling ourselves. And that signature you get if you look down from above on those 3 peaks. And now you can see the atoms that aren't Bose condensed, they're a nice round ball here. The Bose condensate sample, see, it's quite elliptical here. And the reason that's so important is, what I didn't say is in those pictures, we were actually letting the atoms, we'd turned off the magnetic trap. The atoms were actually spreading out before we took a picture of them. Now, that doesn't really change the general features, but what it means here is that if you have a bunch of atoms, normal gas atoms held in a container, and you turned off and let them fly out, there's a basic law of physics that says they'll fly out equally with speeds in the same speed in all different directions. And so the fact this is an ellipse here says these are not normal atoms flying out. This is really a coherent atomic wave that's really spreading out as a wave. That's the only way you can get an ellipse, and so that's really very convincing this is Bose condensation. Okay, so I've been talking all about our experiment, but the basic ideas for Wolfgang used are very similar. A little later in that same year, he made Bose condensates in sodium. Much of the principles are the same. One difference is he started out with a sodium beam and has a counterpropagating laser beam to slow down the sodium beam to load his optical trap there. And then once it's loaded, went ahead and also did evaporative cooling again to make signals like this. And here he had, as I say, his difference, it was in sodium and substantially more atoms than in our first rubidium experiments. Now, that actually sort of takes me up to the first 70 years. I'm going to take just a couple minutes to go to year 71 of Bose-Einstein condensation, because in the following year, there were sort of second generations, both at MIT and at Gila, of improvements of the apparatus that really set the stage then for many of the subsequent experiments use sort of the second generation apparatus. So just to completely take it up to where Eric and Wolfgang can not worry about experimental details, I'll quickly mention these. In the MIT, what they did was change to a slightly different kind of magnetic trap, something called the Yaffe-Pritchard trap. It gave sort of better stability and characterization, substantially improved the number of condensate atoms so they could easily get over 1 million atoms. And so that was kind of the change that they made, and then they did lots of experiments using this cloverleaf magnetic trap. Here's what the sodium apparatus looks like. I think I have it right, that the sodium beam comes in this way. This is a big vacuum chamber here, stainless steel, so big across there. So that's sort of the MIT experiment. The second generation Gila experiment, we went to a double optical trap setup where we have one optical trap here. We sort of collect the atoms, then we push them down, and here we have the magnetic trap. So what you do is you collect a bunch of atoms here, give it a push, flies down, catches here. Do that a few more times to build up more and more atoms down here, where you have very low vacuum. Let's get one more bunch. And so once this is full, then you turn on the magnetic trap. And using this system, we actually also used an old design Yaffe-Pritchard trap we'd been using for a long time for this, but we quickly built this for both top traps and Yaffe-Pritchard traps. They're just good for doing different kinds of experiments. That's not important. It did give us quite a lot more atoms, so now we could easily get 1 million atom condensates here also. And here's what this looks like. This is a completely different scale from Wolfgang's experiment in that we work with just these little glass cells with everything else outside. So now this whole thing is about 10 centimeters across here, glass in there, and then this is all the windings of these magnetic field coils. So with these upgrades, it became very routine from 1996 on to have sort of million-plus atom condensates, and you could use those then for all different sorts of experiments. And that was really the stage for a number of years. I just mentioned in passing that just in the last couple of years, particularly this year, there have now been a whole bunch of new technical developments from all over the world that are going to lead to even better apparatus doing lots more things with, but that's not the point of this talk. So I'll just finish up here by sort of acknowledging that the Gila BEC effort that Eric Cornell and I started in 1990. We've had lots of students and postdocs participating in many experiments. This sort of pioneering beginning work, the particular people were Chris Monroe, Mike Anderson, Jason Incher, and Mike Matthews. So thank you.